Okay, cool. So welcome back from the weekend. Please, once more, we have our exam on Friday, yeah, this Friday, right? Exam 3 is coming up this Friday. I've already posted a study guide, and then the Math Center will have a review session for you guys. I sent you an email. I've already put in the information for all of that, right? So I've solved the problems for the study guide, and I've posted them all on Canvas. So please check them out, right? If you have any questions, do feel free to reach out to me, right? And I can help you out with that. Okay, so now let's continue. Do you have any questions for me? Okay, so if there are no questions, then let's continue from where we left off the last time on Friday. Please, I'm sharing my screen now. If you can't see, do let me know. So what I'm sharing right now is on Friday, we're trying to sketch a curve, right? You're trying to sketch a curve. We learned some series of steps that we have to go through in order to sketch a curve. Right? So just develop those features. And then when you're done, you kind of like combine all the features together, and that will help you sketch the curve. So where we were able to finish with the local extreme values, which was, I think, the F step. This is the last thing we did. 5. And okay, yeah, so we finished this step. Yeah, and then we're able to tell that there's a local maximum occurring at where? At 0, whose value is 0, right? So today we are just going to continue. Since we've done the ID test and then we've done the local maximum and minimum test, the next step is to do the concavity test and the point of inflection. So I'm just going to continue from here, right? So this is still 4.5. I'm sharing the whiteboard now. If you can't see, do let me know. Okay, so we are still on 4.5. So wait, 4.5. And then we are continuing with F prime prime. So what was F prime? So from what we did the last time, let me share the screen for this. Yeah, so from what we did last time, our F, what's happening? Our F prime, yeah, so here's our F prime. Our F prime was given by negative 4s over s squared minus 1 all squared, right? So let me write that there. We have F prime equal to negative 4x over s squared minus 1 all squared, like so. Okay, so let's continue and let's continue with this, right? So now we're just going to get the second derivative. So we need F prime prime in order to do the concavity test, right? So that'll be d over dx of the F prime, so which is negative 4x over s squared minus 1 all squared, right? And then when we get here, we can use the what? The quotient rule. So by the quotient rule, it's just low d high, derivative of negative 4 is negative 4, minus high, so that's minus high, so that's minus 4s. D low, the derivative of 2 s squared minus 1 all squared is going to be 2, and then s squared minus 1, and then to the power 1, and then the derivative of what? S squared minus 1, which is 2x, like so. And then all over, and then we square what is below, right? So this squared. Now this squared will give us s squared minus 1 all to the power 4, right? Now let's simplify this, right? The numerator especially. So we have f prime prime of x equal to, now before I even simplify, I can see that there's a term here which is s squared minus 1, and then s squared minus 1 term here, and then an s squared minus 1. So I can cancel one of the s squared minus 1 for each of the terms, right? Because I'm dividing by s squared minus 1 to the power 4. So I will reduce this, right? So I'll take out an s squared minus 1 from top, or let me write it in this form. I can factor out s squared minus 1 from the top, and then I'll be left with s squared minus 1 all times negative 4, and then let me change this to plus, so 4x, and then this s squared minus 1 will go away, so that will also be 4x, like so. And then all over, I have s squared minus 1 all to the power 4. Please, I hope you see what I did. I just factored out the s squared minus 1, right, from the two terms. right? So from this term, s squared minus 1, from this term, s squared minus 1. So factor it out and simplify what's left inside, right? Now, because I factored it out, I can cancel this one here and reduce it with this, right? Kind of like common factors. So with that one, I'll need to move on to the next slide. So do let me know if you need more time here. Or perhaps I can, this one I have to, I can do, squeeze it a little bit. Let me squeeze it here because it will simplify as we go. Okay, so now let me squeeze it in here. So f prime prime of x will be equal to, now for this one, the s squared minus 1 will cancel out. And then when I look at what is inside this, I have negative 4 times s squared. That'd be what? Negative 4s squared. And then I have minus 1 times 4, which will be plus 4. And then I have 4s times 4x, which will be plus 16s squared. And then all over, since I canceled out one of the s squared minus 1s, the denominator is left with what? S squared minus 1 all to the power 3. Please, are you okay so far? Any questions? And then finally, f prime prime of x will be equal to what? Now at the top, I have 16 minus 4, which will be 12. And then 12s squared, and then plus 4. All over what? S squared minus 1 all cubed. Yeah, so that's our second derivative. Please, any questions here? Is there any part you don't understand? Okay. Now, after obtaining the second derivative, right, we check for the critical points. So for critical points, check for two conditions. We check for where we have a DNE case. But in this case, the only numbers that will make this f prime prime DNE is what? It's 1 and negative 1 in the denominator. But these numbers are not part of the domain. If you remember from what we did the last time, let me show you the original function. I'm sharing my screen, right? You're supposed to see the f, the function f. I think we had it here. Yeah. So we had it here, right? I'm sharing the browser, right? The browser tab. You're supposed to see the function f of x, which is equal to 2s squared over s squared minus 1, right? Notice that the domain excludes negative 1 and 1, right? It excludes negative 1 and 1. So that means that we don't have any critical points for this first case. No critical point, right? But then we check for two conditions. We need to check for the second condition where the f prime prime of x equal to 0, right? So for that one, we need to solve what? 12s squared plus 4 all over what? S squared minus 1 all cubed equal to 0. And to continue, I need to move on to the next slide, but please do let me know if you need more time here. Okay. Now, if a quotient is 0, right, then it just implies that the numerator is 0, given that the solution that we get will not make the denominator 0, right? So the numerator has to be 0. So for this one, if you're trying to solve this equation, we just set the numerator equal to 0. So our solution is 12s squared plus 4 equal to 0, right? So let me just go here. And then I think this time I can partition it in half. We have 12s squared plus 4 equal to 0. Right? Yeah, that's it. Right. But the thing is, trying to solve this, you get 12s squared equal to negative 4. Right? And then when you get to this point, well, let me do this further. So divide both sides by 12, you get s squared equal to negative 4 over 12, which will give you s squared equal to negative 3. So 4 goes here, 1, 4 goes here. So we got negative 1 over 3, right? But then in solving this equation is saying s squared equal to negative 1 over 3. And we know that there is no real number whose square is going to be a negative. The square of a negative number is a positive number. The square of a positive number is a positive number, right? For real numbers. So there is no real number whose square is a negative number. So this one has no real solutions. Right? Now, because it has no real solution, that means we didn't get any critical point for the second condition. Neither did we get a critical point for the first condition. So there are no critical points. Right? Now, when we get the critical points, what we do is we partition the domain of f using these critical points, right? Now, what is the domain of f? From last week, we saw that the domain of f is just negative infinity. We excluded negative 1 and 1. So it's negative 1 excluded, and then 1 excluded to infinity. Now, since we didn't get any critical points, partitioning the domain of f implies leaving the domain alone, because you don't have any point to partition the domain of f with, right? So it's just leave this interval alone. Well, coincidentally, this one also happens to have already partitioned interval. So it's not like it's just going to be one interval. It's going to be 1, 2, 3. The original domain of f is 3 intervals, right? So you just continue through with this, do your intervals, get your f prime prime. So we have, for the interval, you have negative infinity to negative 1. I have negative 1 to 1, and I have 1 to infinity, right? And what's f prime prime? F prime prime of x. That is, what did I get? I have 12s squared plus 4 over, I think, s squared minus 1 all cubed, if I recall rightly. Let me check. Yeah, that's it. Okay, and then from there, from the sign of this f prime prime, we'll be able to tell what's happening with f, right? So let's pick a number. Now, fortunately for us, the numerator here is always square, right? It's always, it's always a positive. I didn't mean it's always, yeah, the x is square, so it's always going to be a positive number, no matter the number you plug in. Even if it's 0, right? There is 4 here, so it's always going to be positive. So now pick a number. Since the numerator is just always going to be positive, you can decide to focus on the denominator, right? If you want, but if you want to, you can check for all of them. All right, so pick a number, negative 2. Negative 2 squared, the top is obviously going to be a positive. And then for the denominator, we have negative 2 squared, that'll be 4. 4 minus 1 is 3. 3 squared is positive. Now the top is positive and then the bottom is positive. So a positive number divided by a positive number is also a positive number. So we know that for this interval, it's concave what? Concave upwards. Let me say upwards, yeah. Now, what about this interval? Pick a number, 0. Now, 0 here is going to make the 12s squared go away, right? You have 12 times 0 squared, which is 0. But then you have 4, so the top is positive, right? The top is positive, but what about the denominator? For the denominator, we have 0 squared minus 1 all cubed. But then 0 minus 1 is what? It's going to be negative 1. Negative 1 cubed is a negative number. A positive number divided by a negative number is what? It's a negative number. So we have what? Concave. Let me just say down. That also works. Now, what about the last interval? For this interval, pick a number, say 2. 2 in the numerator is positive, and 2 down here will be odd. 4 minus 1, which is 3. 3 cubed is positive, so this one is positive. So you have concave up. Right? Yeah, so you've been able to obtain the what? The intervals of concavity. That's all. So concave upwards on this interval, negative infinity to negative 1. Concave downwards or down on this interval, negative 1 to 1. And then concave upward on the interval 1 to infinity, right? And that's it. Okay, I think I see something. So aren't the critical points the paths of the graph where the function goes? Okay, about the oh no. So yeah. So the one that you're talking about, Hunter, is a point of inflection. Is a point of inflection. You see. The critical points are, the point of inflection. The critical points are when we set it equal to DNE or when we set it equal to 0 and so. Do you remember? Yeah. So, yeah. Okay, now talking about point of inflection, we need to do that also on this step, right? So for point of inflection, just replicate this thing that you did here, right? The partition you made for f prime prime. Well, we didn't end up doing any partition. We ended up using the same like interval for the f, right? So it's from negative infinity to negative 1 excluded. Let me do the excluded well, because this may make it look like as if I've included it. Okay, so excluded, so point to, and then 1 excluded, and then to infinity. And then we see that this concave upwards, so you can do CU, concave downwards, CD, and then concave upwards. Okay, so maybe someone will be in a hurry to say that, oh, I see a straight from concave out to concave down, from concave down to concave up. So perhaps there is a point of inflection at negative 1 and 1. But then the thing is that will be incorrect, right? Please don't forget that negative 1 and 1 are not part of the domain. They are not part of the domain, right? So even though we have a straight from concave up to concave down, And from concave up, concave down to concave up, we have no inflection points, right? So no inflection points. Okay. Right. Yeah. And now that we have this information, that's the last step, right? So up to the point of inflection points, and then we move on to sketch the graph. Move on to sketch, right? So E is increasing or decreasing. Step F is local extreme values. E, F, G. G is concavity and inflection points. And then H is sketch a curve. Or someone will ask, so Matthew, are we supposed to memorize all of these steps going into the exam? And then I'll say, no, I'm not going to test you on a graph, right, on the exam, even though you have one on your study guide. So in the solution that I wrote, I told you not to focus on those stuff, right? Don't memorize the step. And in the past, when I usually gave graphs, I would give you an idea of what to do. I'll ask you to do ID test, concavity, and then say, find the intercepts. In addition with the intercepts, try and graph it, something like that. But I'm not going to give you a graph for the exam. So yeah, but at least you have to learn those ID tests, concavity, local extreme values, and then point of inflection, those stuff. Okay, and that's it for this. Please, any questions so far? At this point, you're going to graph, right? You're going to graph. Okay, so let me quickly go to the next slide. Do you need time here? Anybody needs time? Okay, so now let's graph this. Putting everything together. So I'll start with so we have -1, and then we have 1. And then we found vertical asymptotes there, right? From our work on Friday, the vertical asymptote at s equal to 1, s equal to -1. Okay, and then let me go back to some of the information that we acquired for this. I'm sharing you're supposed to be able to see like a web browser with the last week's work, right? With last week's work. I'm going through the solutions that we did and see if we can get some features, some of the features that we had. Okay, so we have a horizontal asymptote, which is y equal to 2, right? So let me add that one. So horizontal asymptotes, y equal to 2. So say 2 is here, right? Horizontal asymptote, y equal to 2. So that's y equal to 2. Okay, now let me switch back and get some other information. Now for vertical asymptote, I know that as I approach, I've already done the vertical asymptote, right? They are negative, s equal to -1 and s equal to 1, right? We did these, but then let's check the infinite limits as you approach either from the left or from the right. So for -1, right? From the right of -1, it is approaching what? From the right of -1, it's approaching negative infinity. From the left of -1, it's approaching infinity. So let me go back. From the right of -1, from the right is negative infinity. From the right of -1. So from the right of -1 is negative infinity. That means it's going up like so. Oh, sorry. What did I say? Give me a sec. No, I didn't. I made a mistake. Erase. From the right of -1 is approaching negative infinity. So if you approach from the right, it's approaching what? Negative infinity, like so. It's supposed to go down like so. Now we have an intercept here, a y-intercept, s-intercept at 0, right? And we have a local maximum here, right? So there's supposed to be a sign like so. Oh no, that's too bad. Yeah, so something like this, right? Local maximum. Okay, and then for the other one, as I approach -1 from the left, it's approaching infinity. So that one is like so for this side. Okay, now let me go back and get some features. For the positive one, let me go to the next. I think it's on the next slide. You're supposed to see the web browser now. I'm sharing the work we did last week. Okay, so now as you approach 1 from the left, it's negative infinity. And as you approach 1 from the right, where is that one? 1 from the right. 1 from the right is infinity. So 1 from the right is infinity. Okay, 1 from the right is infinity. 1 from the right. 1 from the right. Okay, so this is 1 from the right. It's approaching infinity, so that will go up like this. And then 1 from the left is approaching negative infinity, so that will go down. Okay, nice. Now, I know that Let me go to the ID, the increasing, decreasing. I'm sharing the web browser now. That's what you're supposed to see. So let me see the ID test stuff. What is the ID test? Okay, I got this. This is the local extreme value. I've accounted for that. From negative infinity to negative 1, it's supposed to be increasing. From negative 1 to 0, it's supposed to be increasing. Wait, increasing, decreasing, decreasing. Okay. So negative infinity, so more like negative infinity to 0 is increasing, but there's a break at negative 1. Okay, and then from 0 going is decreasing. Okay, so let me check. From negative infinity, okay, to what else? From negative infinity to 0 somewhere, it's always increasing. So that tells me that for this side, it's supposed to be rising. For this side, where there's a break in negative 1, it's supposed to be rising. For this side too, oh, it's increasing. So that gives me an idea that, oh, okay, if it's increasing, then I can kind of like join this. From 0 to 1, I know it's decreasing. So yeah, it makes sense that this is going to fall down and join this. And then from this side too, it's supposed to fall. Okay, now I have a horizontal asymptote at, which is y equal to 2. So the curve can go either this way or that way. For this side, it can go either this way or that way, right? But then let me try and confirm with the concavity results and see how it's going to look like, right? So I need to go back to, concavity, we did it just now. So let me go back here. So I know that it's concave upwards from negative infinity to negative 1. Since it's concave upwards, it's supposed to open up like this, right? For concave downwards, it goes down, it opens down, right? So for concave up from negative infinity to negative 1, let me check. Negative infinity to negative 1. Okay, so I expect it to be opening up. Now, because it's opening up, the graph can go like so before it comes down like so. In that case, it will be like, at this point, it's kind of like when it gets closer here, it's becoming like, it's bending, it's becoming like concave downward kind of. So it can't happen like that, right? So if it's supposed to be concave upward on that interval, then it's supposed to open up. So that makes sense that, oh no, this is too bad. The sketch is not too good. Let me, yeah, so something like this. Nice. So that one is concave upward, right? Now let me go back. Now, from 1 to infinity to is concave upward. Oh, so I expect that the same thing will happen there. Something similar. So that's also concave upward like so. So it holds water. Okay, it's too bad. Okay, so something like, yeah, something like this, right? Yeah, you have a nicer graph on the PowerPoint. Yeah, so we have that also, right? And we also know that between negative 1 and 1 is concave downward, right? So, and you can see that between negative 1 and 1 is concave downward, which is nice. So you have the important features of this graph, and that's how you do it. Please, any questions here? Let me add these things. Let's add this. And that's how you do it. There'll be a nicer graph on the PowerPoint. But any questions here? That's how you sketch a curve. Okay. Anybody needs time here? Okay, then let me switch to the PowerPoint. So I'm showing the PowerPoint for 4.5. Okay, so we did all of these stuff. Yeah, so they're just giving us the information, even function, and all those stuff. Yeah, and then we did the ID test, we did the concavity. Yeah, and this is it. See? Yeah, that's the finished curve. Please, any questions on 4.5? Okay, so that's all. Then let's move on to the next one. Oh, come on. Okay. This is the one. 4.7. Okay, so now we are on 4.7. I'm sharing the PowerPoint. If you can't see, do let me know. So 4.7 is all about optimization problems, right? Optimization problems. Now you notice that later on that with most of the derivatives that we do, right? All the differentiation and integration, we use it in application, especially in optimization, right? So for optimization, we are trying to maximize something. Either we are finding something like an absolute maximum or an absolute minimum kind of thing, right? So let's look at how we solve optimization problems. Now for this one, there's no like, it's not like a cut and dried way, but at least there are steps that you have to follow, guidelines which will apply for each optimization problem that you're going to do, right? So you're just going to go over those steps, right? So to solve any optimization problems, well, obviously you have to understand the problem, because the problem will usually come either is going to be a word problem, or sometimes it's direct though. Yeah, but sometimes you can get a word problem. So you first have to understand the kind of problem you're dealing with, right? You have to understand the quantities involved, what you're trying to optimize, like what are the quantities and all those stuff, right? And then interpret that into a mathematical set of stuff, right? So if it's a word problem, you'll be able to break everything down into something like a mathematical problem, right? So that's the first thing. Now, sometimes to better understand the problem, you can just draw a diagram. Well, it's not all cases you can draw a diagram, but sometimes it is given the problem that you have, you can draw a diagram, which will be useful in your analysis, right? So that's the second step. Now for the third step, you have to introduce notation. You have to introduce notation in the sense that you have to get a variable to represent the quantity you're optimizing. And you also have to get a variable to represent all the other quantities involved, right? So for now, this one says, okay, let's call it Q for now, but you don't necessarily have to call it Q, right? So introduce notation. Now, for all other unknown quantities, you can use, feel free, you can use these, you can use even the, what do you call it, the Greek alphabets, or the Greek letters, or so on. You can use whatever you want, right? So let's say this is the Q, and then we use A, B, C, S to Y to represent the unknown quantities, right? Okay. Now, what you're going to do is, since you are trying to optimize Q, you need to express Q in terms of all the other quantities. So for example, if you're trying to optimize area of, say, a rectangle, and you know the area of a rectangle is what? Length times width. If you let L be the length and W be the width, then your A will be equal to what? L times W. That's what the fourth step is talking about, right? So express the Q, the quantity you are trying to optimize, in terms of what? All the other quantities, right? Sometimes it may not involve all the other quantities, but what I'm trying to say is in terms of the other quantities involved for optimizing that particular what do you call it, expression that you're talking about, right? Or that quantity you're talking about. Okay, so that's the first step. Now, just as I did the example, like the area, if you're optimizing the area of a rectangle, it's L times W, right? You need to have the area in terms of a single quantity, right? So if it's, for example, L times W, you can't optimize it yet. To optimize it, you need the area expressed only in terms of L or only in terms of W. Now, to do that, there is always going to be an equation in the problem which will help you solve for all the other variables in terms of one single variable. So what do I mean by that? So say you are in step 4, you identify your area. That's what you are trying to optimize, right? It's L times W, area of a rectangle, right? Now, you need the area in terms of a single variable, either L or W. Now, for the first step, what he's saying is there will always be some equation such that, let's say somewhere it will tell you L plus W, somewhere in the problem, it could say L plus W is 100. Now, if it tells you L plus W is 100, that means that you can solve for either L or W in terms of the other, right? So you can say, okay, maybe L equal to 100 minus W. And then you can plug this in the area in place of the L so that you get only in terms of W. Or if you prefer, you can solve for W, which will be 100 minus L. Replace the W in the area formula with the what? With the 100 minus L, so that it will only be in terms of L. So that's what I mean by the first step, right? So the quantity you are trying to optimize will then be in terms of only a single variable, a single quantity, right? And there will always be an equation where you can get the other quantities expressed in terms of what? One single quantity, and then you can substitute them back in the equation you're optimizing and get it in a single variable, right? So that's the idea, right? So it says use this equation to eliminate all but one of the variables in the expression for Q. Now, when you do that, as this one did, you see for this one, it eliminated all the variables except for X. So now the Q is in terms of what? A function of X. Now, when you get this thing, right, when you get this function of X, then it reduces to, the problem reduces to optimizing this function, right? Now, to optimize this function, there are three ways you are going to look at. Three ways. When you're on this page, you can't erase. Three ways to optimize this f of x. So I'm going to show you all the three ways. Now, the first way is you can use the closed interval method. If you remember the closed interval method, we did it in 4.1, right? You can use the closed interval method. But this one can be used if and only if there is a closed interval. If the domain is a closed interval, right? Or you can use the first derivative test. Right, for absolute extremum values. And then the last thing is you can use a second derivative test. For absolute extreme values. Okay, so there are three ways. Now I'm going to show you all of these ways, right? Please, any questions so far? I hope you understand. So this is like a summary of what you're going to do, right? Okay, any questions? Anybody needs time here? Okay. Then let's look at this example. So example one, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area, right? So what are the dimensions of the field that has the largest area? Now the thing is, for this one, it makes sense to graph it, right? It makes sense to graph it. So let me do this on the whiteboard. So this is 4.7 optimization, example one. If you want your reference, it's on the slides. Okay, so for this one, let's go back, right? Okay, I think I can get this one. We have a river, so ideally, let me use blue. I have that option. You can use like several colors. So river here, the farmer is fencing, so something like so. Oh, that's too bad. Not good at rectangle. Something vertical, okay, not bad, and then something like so. Okay, so this is the picture. This is what's happening, right? So the farmer is trying to fence this field. Let me come here. Okay, so it says it needs fencing and wants to fence over a rectangular field that borders straight river. The farmer needs no fencing along the river, right? So as you can see, when I did the fencing here along the river, I didn't do any black marking there. I didn't do any straight edge along the river, right? So this is the river, right? So this is how the rectangular field is supposed to be. Now the next step will be I'll try and assign variables, right? So I can say, let here be say x, right, for the length here, which is the width, right, the width of the rectangle. So if here is x, then that place also be x, and then the length is y. Let me say it's y, right? So let me go back. So fencing, fence over rectangle, he needs no fencing along the river. Okay, what are the dimensions of the field? Now, since I'm told the farmer has what 2,400 feet of fencing, that tells me that when I add up all the edges, in other words, the perimeter of this fencing should give me what 2,400, right? So let me go back to the whiteboard. So that means the x plus y should give me 2,400, right? So that means 2x plus y equal to 2,400. So there's one equation, and you can guess what you're going to use this equation for. You're going to use it to solve for one of the variables in terms of the other and plug it in the optimization quantity, right? But before we get there, let's go back to the question. So he needs no fencing. What are the dimensions of the field that has the largest area? So the fact that we are talking about the largest area should tell us that we are trying to optimize the area. So let me go back to this. So let A equal to area, right, of rectangular field, rectangular field. Now, if A equal to the area of the rectangular field, then I know that area of a rectangle is length times the width, right? So in this case, it is just going to be S times Y, right? And then because I will need the area in terms of a single variable, I need to solve for one of the variables in terms of the other. And this one I can clearly get by solving for Y in terms of X here. So from this step, I know that Y will be equal to what? 2400 minus 2X, right? So because I have Y equal to 2400 minus 2X, I can now write the area in terms of only a single variable X, which will be given by X times Y. What is Y? 2400 minus 2X. And so I get A of X equal to what? Now distribute this, you have 2400X minus 2X squared, right? Now, another very important thing you have to find is the domain, right? Because as you saw from the three approaches I showed you, if the domain is a closed interval, then you can use the closed interval method. If it's not, then you have to use either the first derivative test or the second derivative test. So let's try and figure out the domain for this function. And for this one, I'll show you some diagrams on the whiteboard and on the PowerPoint, right? So I'm going to move on there, but please do let me know if you need more time here. Okay. Now let me come here. So let's check the domain. So the domain is, because we define the area in terms of X, we need to consider the width, right? What range of values can the width take? Because the area has been expressed in terms of the width. So now let's look at these examples, right? You can see that the fencing can be done in several ways. We can do the fencing like this, like stretch this length a very long way and then make the width quite shorter. We can stretch the width a bit and then reduce the length as well. Or do it like this, right? Stretch the width more, reduce it. But in either case, the worst case scenario is, since you have 2400 feet of fencing, right? The width of the rectangle, the least you can do is almost as if you just extend the fencing along the river without any width. You see, it has only length without width. That's the worst case scenario. So the worst case scenario is like you give all the fencing. So this is a river, right? So you can't like give all the fencing like this. I mean, the farmer will obviously not do that, right? They need some kind of like side on the width. But the worst case scenario is the width is 0. So that means X has to be greater than or equal to 0. Now, what about the biggest possible width we can have? Well, for the biggest possible width we can have, that means that there will be no length, right? There will be no length. So it's more as if you have the river here, right? And then you have the width like so. So one here, and then another here with no length, kind of like together. Let me say just together. Kind of weird because the person needs a big area, right? But that's the worst case scenario. That's you're giving all the fencing to the width, right? Now, for the width, since there is 2 of them, right? If you're giving the fencing, all the fencing to the width, what is the equation for the fencing? We just saw that 2x plus y equal to 2400. From the problem, we know this, right? So if all the fencing has been given to the width, that means that the length is 0, right? So when y is 0, what do we get? When y is 0, we get, when y is 0, you're going to get what? 2x equal to 2400. So s equal to what? 1200. So that means your x cannot be greater than 1200, right? Your s cannot be greater than 1200. So even if you give all the fencing to the widths, your x is less than or equal to what? The 1200. So you give 1200 on one side and then 1200 on the other side and no width, right? So this tells us that this equation that we have for the area has a closed interval, right? It's from 0 to what? To 1200 for the x, for the width. Please, I hope you understand this. Any questions? Okay, then let's move back to the whiteboard. So for this one, I'll say the domain is from where? 0 to 1200. So that's how I'm getting this. Now, when I get this, I said there are 3 ways to solve this. And I chose this question because this question is a strategic one. With this question, because it's on a closed interval, I can use all the 3 so that you see how each of them work. Now, as I'm going through this, some of the parts will repeat itself. So for those parts that repeat, I'll just write them down, right? And then work from there. So now let's start with the approach. So the first approach, closed interval method. So this one has a closed interval. Please, if it doesn't have a closed interval, you can't use this. You can't use this if it doesn't have a closed interval. So since this one has a closed interval, let's do this. What's a closed interval method? If you remember for 4.1, for the closed interval method, we find a critical point, and then we solve for the value of the function at the endpoints and at the critical points, right? So to find a critical point, we need A prime. So what is A prime? That'll be 2400 minus what? 4x. And then for this one, we need to look for two conditions, where the A prime is DNE and where the A prime is what? Is equal to 0. But in this case, the DNE will not come in because this is what? This number is valid for any x, right? It's going to be correct for any x. There's no undefined case for any x. So we search for this equal to 0. So what does that imply? That implies 2400 minus 4x equal to 0. So if you solve this, you have 4x equal to 2400. And then you have your x equal to 600. Nice. So I have my critical point. Now, when you get the critical point, by the closed interval method, you evaluate the function at the what? At the end points and then at the critical points. Right? Please, before we continue, do you have any questions here? Okay, so let's go. So we are, and don't forget, please, you are trying to find absolute maximum or absolute minimum. In this case, since we are finding the maximum, right? It's supposed to be absolute. It's not a local maximum. We are finding absolute maximum, right? That's why we're using the closed interval method. So now let's go. I have A of 0. Let me check for A of 0. And then I have A of what? What's the endpoint? 1200. And then I need to check for A of what? 600. So for the A of 0, what's the equation for the A? 2400x. So 0, 0. Oh, that'll be 0. But let me write it down. So that'll be 2400, 0. Minus 2, 0 squared. So that'll be 0. Okay. What about this one? That'll be 2400, 1200 minus 2 times 1200 squared. And then 2400 and then 12. For the 2400, this 2 times 1200 squared, I can just do 2 times 1 over 1200, which will give me 2400. So it's just the same thing here. So this is also 0. Or you can think about this. If you assign all the area to the width, what area do you have? If the length is 0, the area is 0, right? If the end is 0, then the area of a rectangle is 0. Okay, so now let's come to the last one. For this last one, we have 2400 all times what? 600, and then minus 2 times what? 600 all squared, right? And then for this one, I think I'm getting 720,000, if I'm right. Let me check. Yeah, so that's correct. Okay, so yeah, so I'm getting this. So clearly from these values, you know that, oh, this is the what? Absolute maximum value. In other words, the largest area possible. But then the question asks for the dimensions, right? It asks for the dimensions, not necessarily the area, right? So let's try and figure out the dimensions. Now, what are the dimensions? The dimensions are x and y. The dimensions of the rectangle are x and y. We've already solved for x, so we know that for x, we have 600. But how do we solve for y? Now, to solve for y, you always have to return to the equation where you solve for y in, right? So we use this equation to solve for y. And we know that y equals 2400 minus 12x, right? So we just plug in the x. So we know that dimensions. So let me say dimensions. Dimensions are s equal to 600. And then since y equal to 2400 minus 2x, we have y equal to what? 2400 minus 2 times what? 600. So that'll give us what? 2 times 600 is 1200, right? So we get y equal to 2400 minus 1200 is still 1200. So the dimensions are what? Dimensions are, you could say 600 by 1200. And that's all. We are done. Please, any questions here? For the other steps, for the other approaches I'm going to do, some of them will repeat right from here. So for that one, I'll just write them directly down, right? So let's look at the other ones. So the other option is you can use the first derivative test. please, if it's not on a closed interval, then these other two ones, the other two I'm going to talk about are going to be very important. Right? You have to use all those ones. So first derivative test. Right, for absolute max or min. Now, the difference between this and the one that we did when we're doing the ID test kind of thing is, this one is not about local extreme values. This is about absolute, right? So please note that. So now let's do the first derivative test. What do? Well, we go through the ID test and then, right, we follow. So let's get the A prime. We need the A prime. So as I said, for some of the results, if they reoccurred, I'll just copy them. A prime is here, 2400 minus 4x, right? So 2400 minus 4x, right? And then what do you do next? You find a critical point. So for the critical points, you're looking for where is DNE and where A prime of x equal to 0. Now for this one, it implies what 2400 minus 4x equal to 0. And that means x equal to 600. So this is the only critical point. And then what do? By the next step is what you partition the domain of the A of x using the critical point, right? But I'll need to move on to the next slide to do that. So do let me know if you need more time. So the domain is what? It's from 0 to, so we have 600 here, and you have what? 1200. And then you partition. So what are you getting? You're getting your intervals. And then the first one is 0 to 600. The next one is 600 to 1200. And then your AX prime is 2400 minus 4x. 2400 minus 4x. And then from there, you'll be able to tell what's happening with A of x. Right, so pick a number. Let me say 1. 1 will be convenient. 1 here, 2400 minus 4 is positive. So I know it's increasing on this interval. Now for this interval, let's pick a number. Let's pick, say, 600. And no, you can't pick that. And 650. Or let's say 700. 700 will work. Now 700 times 4 is 3200. And 3200 is bigger than this. So obviously this will be negative. So it's decreasing. So using the first derivative test, I have this 1200. Now the function is always increasing here and decreasing here. So this function is like so, right? For the entire region below 600 is increasing, right? So from 0 to 600 is increasing. And then at 600, it turns and then it decreases. So that means that point at 600 will be what? An absolute maximum, not just a local maximum. It's both a local maximum and an absolute, right? We're interested in the absolute part, right? So we can say an absolute maximum occurs at x equal to 600, right? So if you want the area at that point, right, at the 600, what's happening there, right? So the absolute maximum value, which will be the largest area, is what? A of 600, which is what we computed, is 720,000. Now, if you want the dimensions, same thing, right? So the dimensions are s equal to 600, and then y equal to, using that equation, you get 1200. So you get what? Dimensions to be 600 by 1200. Please, are you okay with this? Right, so it's just about being able to identify whether there's an absolute maximum occurring at the x, and that's it, right? So let me maybe add this note, largest area. Okay. Please, any questions here? It's 49. Is it almost time? Let me check. How many seconds do I have? Oh, okay. Let me start something. Okay, so that's the first derivative test. Now let's look at the last one, second derivative test. Now this one is one of the easiest that you use, right? Absolute max or min. This is one of the easiest. So for the second derivative test, what do? You first get A prime. And A prime is what? It's 2400 minus 4x. You check for the critical point or set for where this is equal to 0. In other words, this gives us what? 2400 minus 4x equal to 0. So s equal to 600. Now, when you get this, you continue and get the second derivative, right? You get a second derivative. So let me get that. Okay, it's 50, right? I don't even want to spare some seconds. So I have done this on Wednesday when I meet, when we meet, right? And when I meet you, right? You're going to continue from here, right? Thank you for your time. Please look at the study guide questions as soon as you can, right? And if you have any issues, draw my attention quickly, right? So that I can help you with it. So all the best and have a good one. I'll see you on Wednesday.
Thank you, Professor.
You're welcome, Hunter. Yeah, there's no quiz. There's no quiz on Thursday. Yeah, because you have an exam on Friday, no quiz. So that you can devote all the time to review. Yeah, you're welcome.